In this video, I'll derive the equations of motion for the double pendulum using the method of Lagrange's equations. In the figure, we have two masses, mass 1 and mass 2. Mass 1 is connected via a massless rigid rod of length L1 to the ceiling, and then mass 2 is connected to mass 1 through a massless rigid rod of length L2. We can assume that the masses are point masses, which is to say that there's no rotatory kinetic energy or rotatory inertia about its center of gravity, and that gravity is present in the problem. Also, I've given the two trigonometric identities, sine squared theta plus cosine squared theta equals 1, and sine of theta 1 times sine of theta 2 times cosine theta 1 times cosine of theta 2 is cosine of theta 1 minus theta 2. This is also known as the double angle formula, and these will come up later in simplifying some of the algebra. So we proceed by writing our kinematic constraints, and that is to relate the angles theta 1 and theta 2 to the coordinates x1, y1, and x2, y2 using the specific geometry of the problem. Let's write that. Kinematic constraints. And you should be able to see just by inspection here that x1 is just L1 times sine of theta 1. Right? So let's write that down. x1 is equal to L1 times sine of theta 1. And similarly, y1 is equal to negative L1 cosine of theta 1. And the reason for the negative sign is that y is positive upwards and mass 1 is downwards. Okay? And similarly, x2, let me save some space. I'm going to write it here. I'll write it below. x2 is equal to, so it would be L1 times sine of theta 1 plus this distance here, which is just L2 sine of theta 2 plus L2 sine of theta 2, and y2 is equal to whatever y1 was, which is negative L1 cosine of theta 1 minus L2 cosine of theta 2. And let's give these numbers 1, 2, 3, and 4. All right. Now we can find the velocities by taking the time derivative of each of our coordinates. Velocities. And we take the time derivative. So x1 dot is equal to, let's write it as theta 1 dot times L1, sine becomes cosine, theta 1. And y1 is equal to negative, cosine becomes negative sine, so this cancels the negative, and we simply end up with theta 1 dot times L1 sine of theta 1. Okay, and then similarly x2 dot is equal to theta 1 dot times L1 cosine of theta 1 plus theta 2 dot times L2 cosine of theta 2. And then finally, y2 dot is equal to theta 1 dot times L1 sine of theta 1 plus theta 2 dot L2, sine of theta 2. And let's number these 5, 6, 7, and 8. All right, in order now to proceed with Lagrange's equations, we can go ahead and find our kinetic and potential energies. I am going to find the potential energy first because it's a little bit simpler and I can squeeze it in here. So potential energy let me just try and scoot this up a little bit to make some space for myself. All right. And the potential energy we can write as V is just equal to, it's mgh of each of the masses. So it's m1 times g times y1 plus m2 times g times y2. And that is equation 9. And if we take the expressions for y, which are equations 2 and 4, and put them into 9, 2 and 4 can be substituted into 9. And when I do that, I get my final expression for the potential energy, which, let me write it like this. I think I want to group it as V equals minus M1 plus M2 G L1 cosine of theta 1 minus M2G L2 cosine of theta 2. And this is equation 10, and this is my expression for the potential energy. So let's put a red box around that because we'll come back to that a little bit later. Oh, can do better than that. Oh, third time's a charm. There we go. So turning the page, I've gone ahead and copied the velocities from the last page on here because we're going to need this for the purpose of finding kinetic energy, which relies on the velocity. So the kinetic energy and that's denoted T, is just a half mv squared of each of the masses. So it's a half m1 v1 squared plus 1 half m2 v2 squared. And that can be rewritten as 1 half m1 x1 dot squared plus y1 dot squared plus 1 half m2 into x2 dot squared plus y2 dot squared, and we'll call that equation 11. And now we want to substitute 5, 6, 7, and 8, the velocities, into 11. So 5 to 8 into 11, write it like that. And that gives us that T is equal to 1 half. Okay, now we want to expand this all out. And by the way, this is a trig identity. This is just equal to 1. All right, so that is equal to, this just gives us very simply ml squared. So that's equal to, let's write it here. Let's leave it in blue, I suppose. Equals 1 half m1 L1 theta 1 dot squared. That's easy enough. Plus 1 half m2 and I realize I left off my squareds here. That should be squared, and this, of course, should be squared. I don't want to say more than that. Go through it. If I've confused you a little bit, I apologize, but all I did is I multiplied it all out. I expanded it. Okay, and now what I'm going to use are my trig identities to show that that cancels, that's 1. And this here cancels, that's 1 as well. And then this was my double angle formula from before. This is actually just cosine of theta 1 minus theta 2. All right, I'm going to rewrite it all beautifully now, and it should look right. So finally, my final expression for t looks like this. T is equal to 1/2 m1 L1 theta 1 dot squared plus 1/2 m2 times L1 squared theta 1 dot squared. And I left out my squared here, I'm just realizing. This should be squared. And this should be squared. Notice that, please. I left out my squared before, and then this should be squared. All right, so 1/2 m1 L1 squared theta 1 dot squared plus 1/2 m2 times L1 squared theta 1 dot squared plus L2 squared theta dot 2 squared plus this cross term 2 L1 L2 theta 1 dot theta 2 dot times cosine, this is the double angle, theta 1 minus theta 2. And that is our expression for kinetic energy. Let's put a box around that because we'll use that in a little bit. Oh, one more try. And I see a correction here I need to make. I left off my squared sign. Let me just put it back here. Here, right over there, guys. I left off my squared sign. And I think I'm actually missing a closing bracket there. I need to add a second bracket. Yeah, that's right. And I notice as I'm looking at it again, the squared disappeared. I know I corrected it, and then it's somehow, that should be a squared there, is what I'm correcting. The page, I've gone ahead and written down the Lagrangian is just T minus V, and then I've gone ahead and substituted, preserving the blue part, which is the kinetic energy, and keeping the green part, the potential energy, separate. All right, so what remains is to put equation 14 into 15 and solve it for the first equation of motion, which is in the theta 1 direction. Just put that here to remind us. And so let me do this in pieces. So dl by d theta 1 dot is equal to, and I'm going to try to preserve the colors here. So just the part of the Lagrangian that explicitly depends on theta 1 dot. It's that, and it's that. It's m1 L1 squared theta 1 dot, since the 2 cancels the half, plus m2 L1 squared theta 1 dot, plus 2 cancels the half, so it would be m2 L1 L2, and then the theta 1 dot cancels. I'm left with theta 2 dot, cosine theta 1 minus theta 2. Cosine theta 1 minus theta 2. All right, and then we need to take the time derivative of that. That's the next step. So d by dt of partial L partial theta 1 dot. All right, and I'm just taking the time derivative here. So let's group the first 2 terms. That's easy enough. m1 plus m2 L1 squared theta 1. We get a double dot here. And then this term here, I need to use the product rule and then the chain rule. I'm using both the product. Let's do it and we'll mention it as we go. This is plus m2 L1 L2, so theta 2 double dot, times the rest of it, which is cosine theta 1 minus theta 2, theta 1 minus theta 2, and then plus, actually there's going to be a minus, m2 L1 L2 theta 2 single dot, okay? And the reason the minus is because the derivative of cosine is minus sine, so that gives me sine theta 1 minus theta 2 times the derivative of theta 1 minus theta 2 with respect to time, which is theta 1. Let me try to make a little bit more room here. Okay, I'm just going to clean this up, sorry. Theta 1. All right, so this should be theta 1 dot minus theta 2 dot. Okay, minus m1, I left out the dot here. So minus m2 L1 L2 theta 2 dot sine theta 1 minus theta 2 times quantity theta 1 dot minus theta 2 dot. Let's give these some numbers. This would be equation 16. This one would be equation 17. Okay, and then we partial of L with respect to just theta 1. And again, using the colors, trying to preserve the colors. What survives is, let me write it out and then we'll talk about it. But it's minus M2. So it's the Lagrangian with respect to theta 1, and that's what survives, right? So it's minus M2 L1 L2 theta 1 dot theta 2 dot sine theta 1 minus theta 2. And then from the green part, from this part here, we get minus m1 plus m2 gl1 sine of theta 1. Okay, and that is equation 18. And we're just about done. So we now need to take 17 and 18 and put them into 15. So 17 and 18 into equation equals 0. You can just squeeze it in. All right. These terms cancel. This term is just the negative. Oops, let me do it again. This term here is just the negative of that term there. Those cancel. All right. And then we can rewrite this. Let me write it one last time and then we're done. Okay. What survives is m1 plus m2 sine theta 1 equals 0. That is equation 19, and that is your first equation of motion. Let's put a box around it. In order to find the second equation of motion for theta 2, we proceed exactly as we have before, and I copied this down from the previous page, again Lagrangian, only this time we're taking the derivatives with respect to the theta 2 coordinate. The derivative of the Lagrangian with respect to theta 2 dot looks like that. Again, I've preserved the blue color to show which part of the Lagrangian survives. Taking the time derivative of that then yields this equation. And then finally taking the derivative of the Lagrangian with respect to theta 2, the coordinate itself, yields equation 22. And again, I've preserved the blue and the green parts, the kinetic and potential energy parts, so you can see where it comes from. And then finally substituting equations 22 and 21 into equation 15, The two terms with the green lines cancel. We can divide through by L2, and then finally that's what the equation of motion looks like, and we can put a red box around it. And we're done. That's all I want to say about this video. I hope you have found something useful in it. If you had, please go ahead and smash those like buttons so other people can get to see them too. Or better still, subscribe to the channel and be notified of all new videos as they come up. If you have any questions, I'd love to hear from you in the comment sections below. Thank you very much for watching, and I'll catch up with you in the next video.